Okay, let's begin. Let's begin with exercise number 4. Exercise number 4. Exercise number 4. A ring is made of thin wire. And has radius r. I'll use capital letter R and charge Q. Find the modulus of the electric field intensity on the axis of the ring as function of the distance L. The distance L to the center of the ring. Investigate obtain dependence when L is much bigger than R, and define the maximal value of the electric field intensity and the corresponding distance Lm. Okay, I think it is necessary to draw a picture. That explains the situation. So this is the ring. This ring is perpendicular. To the screen. But we can see it. Here. Okay, and I'll define axis x from left to the right. Axis x and axis y. And axis z. Y and z. X, Y, and Z. Okay, so this ring and L is distance between center of the ring and point where we have to find absolute value of electrostatic field intensity. So L is somewhere here. Okay, maybe you have some ideas. How can we find this? How can we find electrostatic field intensity on axis of rings symmetry? Okay, no ideas. I think we can use formula. For absolute value of electrostatic field intensity. it may be defined as dE. dE is equal to 1 divided by 4p epsilon 0, 4p epsilon 0, 4p epsilon 0, and dq divided by r to the power of 2. But this formula is for point charge. But we have charged ring. So how to cope with this? How to cope with this? I think we can correspond infinitely small part of the ring. Infinitely small part of the ring. Here is the radius r. And in this infinitely small part of the ring has charge d. dq. It has charge dq. Okay, so how can we in this way we can define infinitely small part of the ring as point charge. Okay, but how to use this? To find the electrostatic field intensity of the whole ring? No ideas. Okay, but what else? Here in this formula, we have distance r. What is the distance between dq and the point where we have to find electrostatic field intensity? And so the question is how to find this distance. Where will it be on picture? R is distance between dq and the point on axis where we have to find electrostatic field intensity. I think it will be length of this line. This here. So this dash line is equal to r. This dash line is equal to r on the picture, and dE is vector. dE is vector. I'll draw this. dE is if we have positive charge of the ring, that dE will be somewhere here. dE. Okay. Okay, and how to use this? how to use this to find electrostatic field intensity of the whole ring. To find electrostatic field intensity of the whole ring. How do you think? No ideas. No ideas. But first, first of all, we have to take into account that electrostatic field intensity is a vector value. It means that in general case we cannot just integrate this. We cannot just integrate this because this is scalar, but electrostatic field intensity is a vector value. The vector value. It means that we have to do this. Vector E is equal to integral d e x e plus integral d e y j and plus integral d e z k. Okay, so in general case, it is necessary to calculate these three integrals. But there is another way. In this special case on the picture. We don't have to calculate all of them. For example, what can you say about these two terms according to the picture? According to the picture, we can see that system has axial symmetry, and the axis of symmetry is axis x. So electrostatic field will also have this symmetry because electromagnetic field always has the same symmetry as a system which produced this field. The system which produced this field. So according to the symmetry, there will not be these two components. So here we have 0. It is possible to calculate these two integrals, and we will definitely have this result. But to save time, we can notice this fact. Why it is equal to 0? Because of symmetry. It means that for every charge dq here, we can find the same charge at the other end of this ring, and these two charges will produce electrostatic fields. I'll draw a schematic picture. Draw a schematic picture to show this fact. So, the first element dq will produce electrostatic field dE. This will produce electrostatic field dE, and this charge dq will produce electrostatic field with the same absolute value, but with another direction. So I will sign this like dE with head above it, and their sum, as you can see, will be directed in the same direction as axis x. So this means that there will not be projections of vector E in directions y and z, and because of this we have 0 for these two terms. Okay, do you have any questions about this? No questions. No questions. Okay. If there are no questions, I think I will remove this, and from here we can see that E, absolute value of electrostatic field intensity, is equal to absolute value of E and this is equal to absolute value of dE x E, and the absolute value of ort E is equal to 1, because ort is a unit vector. So we have absolute value of integral dEx. Integral dEx. Okay, and to calculate this, we have to find a projection of vector dE on axis x. And how to do this? How to find the projection of this vector on axis x? No ideas. Okay. Okay. We can define some angle beta, we can define angle beta between DE and axis X. And according to the picture, we can see that projection DEX is equal to DE multiplied by cosine beta, and the next step is to define cosine beta from the picture. How do you think? How can we define cosine beta from this picture? No ideas. Okay, but here we have the right angle, with the right triangle. Here we have the right triangle, so from this triangle we can notice that cosine beta is equal to L divided by R. And we may substitute this here and this here, and we will get 1 divided by 4 p epsilon 0, 1 divided by 4 p epsilon 0, L dq divided by R to the power of 3. Okay, do you have any questions about this? Do you have any questions? No questions. Okay, if there are no questions, to proceed, before we proceed, we have to find one more value. We have to find this distance r. We have to find this distance r. And how can we do this? And one more from picture. We can see that here we have the right triangle, and according to the Pythagoras theorem, we will have that this is equal to the square root of L to the power of 2 plus R to the power of 2 plus R to the power of 2. L to the power of 2 plus R to the power of 2. According to the Pythagoras theorem. L to the power of 2 plus R to the power of 2 under the square root. Okay, and this means that here we can write the 1 divided by 4 p epsilon 0, 1 divided by 4 pi epsilon 0, and L dq, L dq, and divided by the square root of L to the power of 2 plus R to the power of 2 plus R to the power of 2, and this square root is to the power of 3. Okay, what questions do you have about this? No questions. No questions. Okay, if there are no questions, we can say that absolute value of, or modulus of vector E, modulus of vector E will be equal to integral of 1 divided by 4 pi epsilon 0, 1 divided by 4 pi epsilon 0, L, and this. This is no bracket. This is no bracket. This is modulus. Okay, and what can you say about the integral limits here? What about the integral limits? No ideas. Here we have to add all charges dq, and if we add all of them, we will get charge q, charge of the whole ring. So integral limits will be from 0 to q. From 0 to q. Okay, and if we see carefully on this integral, we can notice that 1 divided by 4 pi epsilon 0, L, and this root don't depend on element dq. They don't depend on element dq. And moreover, all these values are non-negative. So it means that we can write them outside of the integral and modulus. 1 divided by 4 pi epsilon 0, 1 divided by 4 pi epsilon 0, L divided by square root of L to the power of 2 plus R to the power of 2. And this is to the power of 3. To the power of 3. And the absolute value of the integral from 0 to q, d q with head above. And this integral is easy to calculate. It will be just absolute value of charge q. It will be just absolute value of charge q. So we have here we have just this, just it, and absolute value of charge q. Absolute value of charge q. Okay, do you have any questions about this? So here we have we have found absolute value of electrostatic field intensity on the axis of the ring. On the axis of the ring. So we have found that E is equal to this value, equal to this value. E is equal to this value. Okay, and do you have any questions? No. So I will remove some things. I'll remove some things that we don't need more. And to clean some place. And what can you say? What can you say if we have to find electrostatic potential, electrostatic field potential? How to find this value? Electrostatic field potential. Okay, I think it may be. I think it may be done in the same way as it was for electrostatic field intensity. Electrostatic potential that produced by elementary by this point charge dq is equal to 1 divided by 4p epsilon 0 and multiplied by dq and divided by r. And r is equal to square root of L to the power of 2 plus R to the power of 2. So we can notice that it is 1 divided by 4p epsilon 0 dq divided by square root of L to the power of 2 plus R to the power of 2. Plus R to the power of 2. And as you can see, this is electrostatic field potential that produced by this element dq. But how to find electrostatic field potential that is produced by the whole ring? How do you think? from here? No ideas. I think it may be found just by integrating this, because electrostatic potential is a scalar value. So we can just add them like simple, no, like numbers. We can just add them like numbers. So we have phi is equal to integral from 0 to phi d phi with head above, and this will be equal to the integral from 0 to some q, and here it is necessary to substitute this. For p epsilon 0 and square root in the integrand don't depend on charge q. So this means that we can that we will obtain just this, but without d in front of q. So this is electrostatic field potential on the axis of this ring. On the axis of this ring. So we have found electrostatic field intensity and electrostatic potential on the axis of the ring. But it is impossible to find this in the other points in space, because to do this, if we try to do this, we will meet elliptical integral, and elliptic integral cannot be expressed in elementary functions. It cannot be expressed in elementary functions, so we will just find electrostatic field intensity and electrostatic potential on the axis of the ring, but not in every point of space. So here we have found two values: electrostatic field intensity, its absolute value of electrostatic field intensity, and electrostatic potential. Okay. What else it is necessary to do in this exercise? What else it is necessary to do in this exercise? It is also necessary. It is also necessary to find. It is also necessary to find. Also necessary to investigate obtain dependence when L is much bigger than R, or much larger. Yes, because large number, it means that L is much larger than R. Which conclusion can we make from this condition? From this condition, we can make a conclusion. We can make a conclusion that the square root from L to the power of 2 plus R to the power of 2 and to the power of 3 is almost equal, or approximately equal to square root of L to the power of 2 and to the power of 3. And this will be equal to L to the power of 3 absolute value. But L is distance, so this is non-negative value, and this means that its absolute value is equal to this value. So we will get L to the power of 3. You'll get L to the power of 3. And from here and here, in this special case, we'll have that E equal to this, and this will be approximately equal to 1 divided by 4p epsilon 0, 1 divided by 4p epsilon 0, and L absolute value of Q divided by L to the power of 3. And this will be equal to 1 divided by 4p epsilon 0, absolute value of Q divided by L to the power of 2. And as you can see, we have obtained the same formula as formula for electrostatic field intensity of point charge. And this is good because it means that from a very far distance, this charged ring looks like a point charge. If it is looked from it is if it is if you look on this ring from a very long distance, we will see something like point charge. Okay, do you have any questions about this? No questions. Okay. If there are no questions, let's continue. In this exercise, it is also necessary to define the maximal value maximal value of the electric field intensity and corresponding distance Lm. So it is also necessary to find maximal value of this. How can we do this? How can we find this maximal value? It is according to our calculus course. According to calculus course, how can we find maximal value of a function? It is necessary to calculate the derivative. To calculate the derivative. It is necessary to find the derivative and make it equal to 0. dE by dL, or derivative dE with respect to dL, and it will be equal to dE and dL, and here we have this in brackets. We have this in brackets. So the next step is to notice that charge Q and 4p epsilon 0 don't depend on L. So these values may be written outside of the derivative. So absolute value of charge Q divided by 4p epsilon 0, 4p epsilon 0, d and dl, open bracket, L divided by the square root of L to the power of 2 plus R to the power of 2. And this is to the power of 3. To the power of 3. Okay, and the next step is to find this derivative. How can we do this? To define derivative, I think we can just use simple rules from calculus course. To use rules from calculus course, and we will get first term will be 1 divided by the square root of L to the power of 2 plus R to the power of 2. R to the power of 2. And the next term will be plus L multiplied by derivative of 1 divided by square root to the power of 3. square root to the power of 3 in the denominator is the same as value to the power of minus 3 seconds. So it will be, this derivative will be minus 3 divided by 2, 1 divided by the square root 3 second minus 1 is equal to minus 3 second minus 1 is equal to minus 5 second. So here we will have L to the power of 2 plus R to the power of 2, and this to the power of 5, to the power of 5. And under the square root, we have to we also have function of L. It means that we have to use the chain rule to calculate this derivative. So it's necessary to multiply this by 2L. Okay, let's simplify. Let's simplify this expression. Oh, here I have forgotten. It is to the power of 3. Let's simplify this expression. Let's simplify. So it will be minus 3 L to the power of 2 divided by square root of L to the power of 2 plus R to the power of 2. And this is to the power of 5. To the power of 5. Okay, and it is necessary to simplify this again. We can notice that mutual denominator will be this square root to the power of 5, and this means that we can write this without changes, and here we will have L to the power of 2 plus R to the power of 2 minus 3 L to the power of 2, and divided by square root of L to the power of 2 plus R to the power of 2, and all this to the power of 5. And this will result R to the power of 2 minus 2 L to the power of 2 divided by this square root to the power of 5 to the power of 5 Okay, do you have any questions? No questions. No questions. If we have maximal value, it means that it is necessary. The necessary condition of maximum is the derivative is equal to 0. So it is necessary to put this equal to 0. Put this equal to 0. And from here, we will have the equation, to find this value Lm. Lm is a value of L that corresponds to maximal value of electrostatic field intensity. So from here, if we solve this equation, we can see that Lm is equal to plus or minus square root of r to the power of 2 divided by 2. We have two roots. We have two roots for this equation, but as you can remember, L is distance, but distance is a non-negative value. Distance is non-negative value, so we have to leave just positive root. It is necessary to leave just positive root. And because of this, we will have absolute value of r divided by 2, and r is r is positive, so we can rewrite this as r divided by square root of 2. This is a value of distance Lm that corresponds to maximal value of electrostatic field intensity. And you can see it is possible to notice that the derivative changes its sign at this point. So Lm is corresponding value to the maximum of electrostatic field intensity. Okay, and the last is to find maximum value of electrostatic field intensity. How to do this? We can use this formula. And according to this formula, we'll get that we'll have I'll just rewrite this to make it clear. So here we will have Lm instead of Lm. Okay, and let's and here we also have Lm. Let's substitute with this. Substitute this. So 1 divided by 4 square root from 2 p epsilon 0, for p epsilon 0, r absolute value of q divided by the square root of r to the power of 2 divided by 2 plus r to the power of 2 and the square root is to the power of 3. Okay, it is necessary to simplify. It is necessary to simplify this expression. So we will get this. I will get this, and here r absolute value of q divided by the square root of r. It will be 3 r to the power of 2 divided by 2, and this is to the power of 3. Okay, let's do the next step. Here we will have the same situation. And square root of 2 to the power of 3 r absolute value of q and divided by the square root of 3 to the power of 3 and here and the absolute value of r to the power of 3. And let's simplify this. We can divide this and this. So we will get 1 divided by 4p epsilon 0, 4p epsilon 0, and square root of 2 to the power of 2 r absolute value of q and 3 to the power of 3 is equal to 27. And 27 is equal to 9 multiplied by 3. So we have square root of 9 multiplied by 3. And the absolute value of r is equal to r, because r is always positive. Because r is always positive. R is always positive. And so it will be here to the power of 2. It will be 1 divided by 6 square root of 3. 6 square root of 3. 6 square root of 3 p epsilon 0 p epsilon 0 absolute value of q divided by r to the power of 2. R to the power of 2. So this is a maximal value of modulus of electrostatic field intensity. Okay, do you have any questions about this? No questions. No questions. Okay, if there are no questions, I think that we can that we can that we can finish for today, and I'll just think I just say that you can do some exercise. You can do some exercises at home, and there will be exercises from electricity and magnetism. From electricity and magnetism, exercise number 2 and number 3 from electricity and magnetism. You can do them as a homework. Okay, do you have any questions?
No, thank you.
Okay, if there are no questions, so thank you for your attention. Thank you for your attention, and I hope to meet you next week.
Окей, thank you. Тоді до побачення.
Yes, okay. Have a nice day.
Have a nice day.